Good morning, sir. Good morning, Dr. Sarkar.
I think Dr. Sarkar, are we audible?
Good morning, Aditi. How are you? I am audible. Yes.
Good
Yes.
morning, good morning. Yes,
You are
sir.
audible. Yeah, yeah.
Okay, sir. We were
Welcome, sir.
just checking up.
Yeah, yeah, yeah.
Hello, Dr. Yunus Ali. Welcome. Namaste, salam, good morning. Many thanks for joining on time. We are waiting for a couple of minutes as more number of participants going to join. Very excited to see very interesting list of people joining, researchers, practitioners, decision makers. Dr. Yunus Ali, good morning. Are you able to hear us?
Yeah, very good morning.
Thank you so much. Thank you, Rocco. Okay, I think Dr. Sparsha will join soon. So let's start. Feeling so good. Welcome to our webinar session on understanding landslide and associated risk factors for enhanced preparedness. Landslide have long been a growing concern, but the acceleration of landslide event is an reality. Their frequency, impacts, and geographic spread are increasing. We constantly hearing this in news and in our research in many ways in different research data and that. We all are involved directly or indirectly in landslide risk management that require a holistic approach that combines scientific understanding, community engagement, and proactive planning to safeguard lives and livelihoods. There are many interesting initiatives have been taken by many organizations, our authorities, research institutions, academic research, and that. This webinar session is joint efforts by the organizational team of Miyamoto International, Norwegian Geotechnical Institute, and AIDMI. As climate change continues to alter weather patterns and increase the frequency of extreme events, The importance of effective landslide risk management has never been more pressing. Today, we are honored to have a distinguished experts who bring a wealth of knowledge and experience in this field. Their insights will shed light on innovative strategies, good practices, and collaborative approaches that can enhance our preparedness and response to landslide risk. We look forward to their perspective on topics such as present scenario, critical lessons, and modeling. Mihir Bhai's schedule has been changed because of his long distance air travel. So he may join later on stage or maybe not, just got news in the morning. However, behalf of All India Disaster Mitigation Institute, welcome you all. This is really, exciting panelists and expertise we have, not only in the panel, but also in the participants. We are very much looking forward for this discussion and carry forward these things in a continuous basis. This is not one time, but it is a joint efforts. Each of us can contribute and join. With this, I would like to request Dr. Shantanu Sarkar for keynote address. Dr. Sarkar is the director of Uttarakhand Landslide Mitigation and Management Center, India. Dr. Sarkar is with more than 3 decades of professional experience, actively contributing in the field of disaster mitigation with focus on landslide research with reference to mapping, monitoring, slope stability, and risk assessment. Dr. Sarkar is pioneer in initiating landslide hazard zonation in early 90s. Engineering, geology, remote sensing, and GIS application are his high interest and engagement with range of stakeholders in India and outside. Dr. Sarkar, thank you for taking out time and for keynote address. Over to you, sir.
Okay, thank you. I am audible?
Yes, sir.
Okay, fine. So, thank you very much and a very warm good morning to all of you. I thank Miyamoto and ADMI for giving me the opportunity to speak on my favorite subject. So I could see some of the participants and organizers whom I know very closely. So without wasting time, shall I start presentation? And
Please, sir.
okay, fine. So, can I see this? I think it's my screen you all can see.
Yes, sir. It's
Okay,
full
fine.
screen. Thank you.
Okay, thank you. So, uh, because time is too short, so I'll be speaking little fast and I'll try to speak on several aspects of landslide disaster mitigations. As you know that I was working as a chief scientist in CBRI, and after retirement, I is re-employed and engaged in establishing a landslide mitigation center at Dehradun and under the Uttarakhand government, under the Uttarakhand State Disaster Management Authority. So I am trying to, do several things related to landslide and new things can happen here. Okay, so let's start. So within this 15 minutes of my talk, I'll touch upon the landslide prevalence in Himalayas, something on landslide susceptibility and hazard mapping, landslide forecasting, which is very challenging aspect of landslide studies these days, mitigation measure, and disaster risk reduction for hill townships. When we say that the landslide, disaster mitigation, so broadly we can have, this six aspects, which I think is very important. One is that you should have a landslide information database, very good database. Without that, we cannot do anything. Then we have landslide hazard and risk assessment. Then landslide investigation. Then do the stability analysis and mitigation measures. And then other is landslide monitoring, early warning. And the last one is very important. And, I am trying to do it in our state, that the awareness and preparedness. So, as everyone knows, that 15% of the land area covering so much of million square kilometers affected by landslide, as given the report by NDMA. And here you can see that these are the three major parts, in the Himalaya, the two parts in Himalaya and Western Ghats, which are affected by landslide. Now I'll show you some examples of landslide problems in Himalaya, particularly along the road. So I'm going back to, in 2001, in the landslide which we have studied and did some risk assessment. So this is a Fata landslide, which is near Gaurikund, going to Kedarnath Road. There's a huge debris flow, and there were casualties. Then coming to the persons who are working in landslide must be knowing about that very famous Uttarkashi landslide that is named as Barunavat landslide. And you can see the picture before the landslide occurred and after the landslide. Though there was no casualties at district administration, and we are also there at the time in 2003. We could save life, but there are huge damage of the buildings. And the persons who are working in landslide, they must visit this Barunavat, because after that, with GSI and THDC, they have implemented several measures. So that, so all the measures you can see there, and whether it is a short fitting or rock bolting or soil leveling, all the measures were being implemented there. This is also another disaster in 2009, that is debris flow in the Pithoragarh district, where around 4 villages swept, where more than 50 casualties were there. Now coming to the present days landslide which is happening, I mean this year, this monsoon only. So this is Patalganga slide, which is a rock slide, and you can see this, that the tunnel which was damaged due to this landslide. And if you have good data, other satellite data, Google data, you can look back that the what is the condition or scenario, whether the landslide is diminishing or it is increasing, and several things. So this is another landslide, which is Sonprag landslide, which also occurred in the last month only, and there is a huge damage to several things in the Kedarnath Valley. So if you just look at this landslide in 2012, hardly you can see this landslide, right? And again, 2014, you can see that there's this landslide. You can see very well. It's a huge landslide. Maybe it was reactivated during the 2013 Kedarnath tragedy. And again in 22, you can see that most of the part of the landslide is already stabilized naturally. And again this year it is again activated. So you can see it is a dynamic process. You if you think that the landslide is stabilized, but you don't know that when it will reactivate, right? Then apart from this, the landslide is happening in the road and national highways. Everyone knows it. Everyone get the news. But there are some landslide which is occurring in a very remote villages, right? So here you see that in the Dhansali district, in the Tehri districts, some landslide occurred, and there were casualties, and people lost their homes. So this landslide, whenever it is occurring, our team is going there to see that what can be done, will be the next action plan. So those type of landslide, which is not in the townships or not along the road, but they are in a remote village. So that is also very challenging task to do something for them. This landslide, this is some data of some frequency of landslide. Last year, we reported around 3,800 landslide. This year, up to August, it is 1,001. but the data is a little higher side, because the data which we are getting from different departments, even if there is a small failure or some rock slide or some road blockage, they report it as a landslide, but truly it is not landslide. So what I am trying, that I am developing a database which only have the major landslide, which is very important. So this way I am trying to have this digital database, so that we can prioritize the things, we can apply some warning system and monitoring part and all those things. So I am only concentrating these days on major landslide, which is either affecting the towns or roads, or some infrastructure. Now, what I want to say, that in between all this landslide, some and 10, 15 years, there was a sudden the big disasters, right? So if you look at, this is the Kedarnath disaster, though it was a basically a flash flood, but along this flat path there are a lot of landslide debris, and a lot of debris slide also occurred. Okay, so this is one thing, one disaster. Again, in 2021, again, in February, there's a major disaster known as rainy disaster. And this is again is a flood, but actually it was triggered by a rock slide, a huge rock slide which fell down in a glaciated valley, and then after that, there was debris and mud and so many things, and so many people died, who were trapped in the tunnel. Also, everyone knows it. And then about this Wayanad landslide, everyone knows. Now the debris flow, and it was really is a big, big disaster. So you can see that apart from several disasters, which can be controlled or which can be minimized, these disasters we don't know. I mean, it's a very challenging task. What we will do? What has to be done? I mean, we are helpless. Sometimes I think like that. Okay, so these are some of my views on this. And apart from that, now you can see here this landslide. There are some landslides which are occurring inside the town. Okay, so this is in the Dharchula, where you can see that the landslide has occurred. It's the big boulders, and the whole town is in risk. Now we are we have investigated and trying to implement the design measures. Then again, in a Nainital town, there is a risk here for the rockfall. So that also we are taking up. And in Haridwar also, there are several unstable slopes. Okay, so these are the some of the landslide and slope related problem inside the town. That is very important to tackle. And about Joshimath, everyone knows that in 23, there's a large subsidence, and though there are no specific landslide, but there is a ground subsidence, and there is a lot of houses got damaged. So what we are doing now, that we are completely changing the surface drainage system there. We are constructing new sewerage network there. We are protecting the toe erosion of Alaknanda River, and also slope stabilization. And this is the beautiful contour map of very high resolution dam, and where the buildings were classified into different classes. Okay, and the administration is taking care of demolishing the red building which is completely damaged, and the buildings which can be partially damaged can be retrofitted or not. Again, in other towns, so it's very surprising, that other towns also I'm seeing the same thing. I mean, there is a lot of subsidence occurring. There's a damages in the contract. There are 35 houses we got damaged, and if there is no landslide, this is only subsidence phenomena. There is a differential settlement, due to water problem and other things. Okay, now coming to another topic of landslide susceptibility, hazard, and risk assessment. As everyone knows, that risk is hazard is a function of hazard, vulnerability, exposure, and for different disaster, people calculate the hazard and risk in a different way. But when we talk about landslide susceptibility, that means that this is for the student, that we are only talking about the landslide potential areas. We are not talking about the hazard, right? Because if we talk about the hazard, then the time factor has to come in. Okay, and it is very difficult to do the hazard assessment, because in India, in our country, we don't have the frequency data records of landslide. So without that, we cannot do anything related to hazard assessment. But of course, we can do the susceptibility study and then go for risk assessment. Now, this is a landslide susceptibility map created by Geological Survey of India. Dehradun, and you can see that there are 3 classes. But this type of donation map is very, it's a low, very small scale. We need to create large scale maps. So people are doing. I mean, many institutions are doing this work. Then now, this I want to share. One of my PhD student has done this work, that he has tried to do the hazard mapping, right? In India, very few persons have done this work. So he could collect some data from 71 to 21 in the Kalimpong region and try to uh, establish the hazard and temporal record of landslide inventory, and then he has done the landslide susceptibility map. Okay, and then for space-time landslide hazard mapping for in the probabilistic model, we can calculate the 5 years, 10 years, and 15 years probability of hazard mapping. So this way, you can work on hazard map, and once hazard map is there, then with the land use practices like different risk elements like habitants, agricultural land, forest, and other things, you can work on a landslide risk assessment. So this is one thing I would like wanted to share you. Then another, I should talk about something on landslide forecasting and warning. This is very, very important, and we are struggling to really do this warning system. I know that some of the institutes in India are working on that, but the problem is that there is a ground-based monitoring system, but how the best way that we should monitor the climate, and then if we know the hazard areas, then we can have a warning system. But basic idea is that we want to do this because the triggering factor is mainly rainfall. So you need to collect the rainfall data and landslide data here, so that you can have a rainfall threshold and do the analysis part. In literature, you will find not many threshold values, for different countries, different regions, and basically it is based on 2 types of model. One is event duration and another is intensity duration. So event duration means you are working on a cumulative effect of rainfall, and intensity means you are preparing establishing the threshold based on the how much rainfall is occurring within 1 hour or in the minutes, like that. So in this way, people are working on that. And if we see the monitoring of landslide, there are basically 2 things. One is ground-based and another is satellite-based. For ground-based monitoring, in the landslide part, you install several instruments like piezometer, inclinometer, seismometer, and many instruments, and you observe it. You 24/7 get the data, and when there's a threshold level crossed of the movement, then you can send the warning. The other part is that you can have a insert data, use of insert data for landslide. Basically, this type of insert data is good for it's a little bit large area, deformation pattern to see in the cities. Like I will say, this is the this one is the example of Joshimath town, where the Indian Institute of Remote Sensing Dehradun did this INSAR study, and you can see that the red patch where there were maximum subsidence was there. So within a period of 6 months, they analyzed the INSAR data and got this result. So INSAR data is very good. Without going to the site, you can do this analysis, but it is good for when you are studying a large region, particularly the towns. We have also done the same student has done. This is the Pakyong airport, and by analyzing the insert data, you can see that the red patch of the airport where there is a subsidence, and we worked there in the Pakyong airport for a few years, for 4 or 5 years, and monitored this ground subsidence, right? And you can see that this ground subsidence, which is shown here, is a blue square, because whenever we have taken reading, this is the data. But this is very well matched with our satellite insert data in analysis also. So with insert data, you can have a continuous monitoring of this type of infrastructure or major important area. Now, coming to mitigation, I'll just quickly go that for mitigation, everyone knows that you need to investigate very carefully the landslide, because as I'm seeing here that there are a lot of mitigation measures going on by several departments, but the sometimes lack due to lack of good investigation, we arrive at good wrong measures. So investigation is very important, and then you do the analysis, and then basically you based on the stability analysis you have several designed several mitigation measures. And what I mean to want to say here, one important thing, that whenever you are doing the mitigation measure, you have many options of mitigation measures. So we have to very cleverly select the right adaptable mitigation measures. Okay. And then, okay, this I want to see that this is the Balianala landslide, which is, from 19, I think from 1900 something, it started here. And there's now we are implementing several measures, and whether it's the SDA or it is the grouting work. And you can see here that we have a part of the landslide has been, there are many mitigation measures like creep work, SDA, shortcutting, micropal, everything is we are implementing so that we can stabilize. But the challenging part is that when we design before excavating and starting this mitigation measures, the scenario is different, and as soon as we discover the thing, the scenario gets changed. So it is a very challenging, but every time there's a geological surprises. So we have to ready with that how quickly we can modify the design and apply it to the ground. That is also very important. Now coming to this last part is the disaster risk reduction for hill townships. What we are doing now, that we are doing the LIDAR survey. I mean, planning to do, we will start. We have not started yet. LIDAR survey of all the important hill towns, so that we can have a very good, database with the digital elevation model, surface model DTM with the contours, large scale contours and high resolution orthophotos, which can be used not only for any risk assessment, but it can be used for some other purposes also, like town planning, some infrastructure construction, anything you want to do in the hill town, you need this base data. So we are planning to do it. So far in India, such type of high resolution dam for the hill area is not available. And okay, I am not going to in detail for what is a LIDAR survey and all, but we know that there is airborne LIDAR also and terrestrial LIDAR also. And the best part of the LIDAR is that it can penetrate the vegetation. So we can really form a very good DAM with the LIDAR survey. And okay, fine, this I'll skip. So it is the example of LIDAR survey in the of your Joshimath town. And even these are the cracks which can be also, major cracks can be identified from this orthophoto and sorry, LIDAR data. And this is showing the bare earth dam with built up remove. So we can remove the built up part and then see the ground. So we can have an actual digital elevation model and very good contour map in a centimeter resolution. So this, you can see that how beautiful is this orthophoto of the Joshimath, where you can map all the buildings, road, and plan for the future. Now we in the first phase, my center is taking up this 5 towns for LIDAR survey, and along with that, we are also doing a complete geo investigation of these major hill towns, and this will include all geological, geophysical, and geotechnical at a selected sample point, so that we can build a very good geo database of all the towns. Why it came to our mind that when we wanted to do quickly some work on the in Joshimath, we find that there is no data, no good data was there to construct or analyze anything there. So then we decided that okay, let's start from here. We'll do the we'll have a good geotechnical, geological, and all the data for all the major towns and all the departments, whether it's the PWD or the irrigation or the tourism, all departments are looking at us that when we do this geodatabase, then they can also use for their own department. So this is not only for the landslide hazard and risk assessment, for other applications also. So with this, in the concluding remarks, everyone knows it, that we're trying to do now, that application of scientific engineering knowledge into practice, assessment and hazard, and also is very important that you should have a very good interpretation on the possible consequences, because a landslide and other always have a cascading hazards. That part is in a, these days people are talking about multi-hazard. So I am talking about that only. Instrumentation and threshold based early warning is very good, and it is a very challenging part. So far, we are working very good in the hazard and risk assessment, mitigation measures, but this part of early warning is still is a long way to go. Then geo investigation, landslide risk assessment, as I told you, enforcement. This is another important part which I am coming into the center. I am finding in the enforcement of building codes and good construction practices, because I found that in Josima town, I know the bearing capacity is hardly 10 ton per meter or something like that, and people are building 5 stories and 6 stories building. So that is also very important part. And proper land use plans, and this community preparedness awareness building. We are trying to do a lot of trainings at the panchayat level and the village level, so that people can understand the disaster, and so that they can save their own life also. So with this, thank you. So I am done. I don't know whether the
Thank you.
time was okay or I have taken more time, but
Well,
I have several
it
things to say, but time was too short, so I thought that I will discuss it.
Thank you, Dr. Sarkar. It's really in depth and covering wide range of aspects that needs to be there. So yes, it took a bit more time than expected, but very valuable
Sorry for
insights. But very valuable insights. So I didn't, interrupt into that. Thank you. Especially for highlighting the areas like how important is database creation, and thank you for initiate that thing, and also about the importance of landslide investigation. In the chat box, I have shared recent this global assessment report by UNDRR, which again emphasizing on foreign method. Again, for us as a practitioner, as a researcher, program designer, we need to understand the dynamic process of landslide, which you explained, which is very much important for all of us. Also about the towns, urban areas, and that also linked with very old case of Nainital landslide in 1880. So thank you for reflecting these things and also emphasizing on our way ahead aspect of early warning thing. We encourage everyone to participate. Use the chat box with your comments, questions, and inputs. We will have some time for open discussion. However, we encourage you to write down your question and points in the chat box and not wait until question answer session. With this valuable insight, let me invite Dr. Yunus Ali from Indian Institute of Science, Education and Research, India. Dr. Ali's research specializes in geomorphology, remote sensing, machine learning, and GIS to analyze natural hazards, particularly landslide and post-seismic landslide controls, river and coastal morphologies from local to regional and global skills. Dr. Ali is going to share the critical lessons from the Wayanad catastrophic debris flow disaster based on his recent engagement. Over to you, Dr. Ali. Thank you. You are mute, sir.
Thank you, Dr. Vishal. Am I audible?
Yes, very much clear.
Yeah. Thank you, AIDMI and Miyamoto, for giving me the opportunity to present my results, research result on the Wayanad landslide. Professor Shantanu Sarkar has covered the basics for me comprehensively. So here in my presentation, I will briefly document what has happened in the Wayanad during the July 30, 2024. A fourth topic today. So we did a comprehensive field work in the region.
I think we lost him. Yes, I think must be some technical issue with Dr. Ali, not able to hear. Okay, waiting for one more minute. Otherwise, we will move ahead. And once he joined, can restart.
Vishalji, we can
Yes.
have Sparsha because
Oh.
some internet connectivity is the issue we have
Okay.
encountered with Dr. Yunus.
Oh,
So
okay. Right. Is Dr. Sparsha here?
Hi, can you hear me?
Yes, very
Vishal?
much clearly. Yes, thank you so much. Thank you for joining. And can we ask you to have some change in the sequence and take your session first?
Sure. I can do that. Let me just try to share my screen.
Meanwhile, let me introduce you, Dr. Sparsha Sinduri Nagula, with a geotechnical engineering background and associate with Norwegian Geotechnical Institute in Norway. Dr. Shah specialized in computational geomechanics, and many thanks for taking out time to join us. Over to you, Dr. Sparsha.
Yeah, thank you, Vishal. Thank you so much for the nice introduction. Very good morning to everybody. Hopefully I'm audible. Just in case if you cannot see my slides or something
Clearly.
doesn't move, Vishal, just let me know or let
Yes.
Vishal know about it.
Yes.
So I am Sparsha Nagula. I work at the Norwegian Geotechnical Institute in Oslo, Norway. I come from a background of civil plus geotechnical engineering, and I mainly work in the field of computational geomechanics. So I basically simulate boundary value problems in geosciences. So today, like Aditi kind of said that I should talk about something which comes from my own background, which is computational geomechanics, and definitely we're talking about landslides. I try to kind of keep the talk a bit more general and try to give you an overview of what tools do we have available in case of numerical modeling, and at the end we try to sum up why numerical modeling is basically kind of important. So when you talk about landslides in general, there is a lot of different packages which are involved, which Shantanuji very rightly kind of introduced during the keynote today. So we start, and they are like a chain of events that we kind of have to follow, which kind of includes the hazard mapping, which includes the susceptibility mapping. Then we probably are looking into a numerical model where we try to kind of assess some of the critical slopes, whether they're how critical they are and what a failure could lead to. And then eventually we go into designing mitigation measures, and then we probably end up developing early warning systems. So what we need to kind of, I want to highlight is all of this kind of goes into a bunch. None of it is actually independently important to or enough to basically solve the problem at hand. So we have to put them all into a package, and then probably the weightages for each of the things kind of changes depending on the situation at hand. But you basically have to put them into a package to kind of arrive at a solution. What we are going to talk today is about, let me choose a pointer. Yeah, today is about the numerical part here, which is point number 2. So when we talk about numerically modeling a slope, the first thing that comes to our mind or should come to our mind is the scale that we are trying to operate at. So it's either you start at a global scale, at a very, very huge scale. For example, this is a snippet of a map which NGI developed along with CDRI for the entire globe to map the landslides occurring due to rainfall and earthquakes together. So the red areas are the areas which are basically susceptible to landslides. So here we used a mix of, I would say, very precise engineering kind of decisions and also some kind of physically based models to assess which areas are kind of prone to landslides. And then we start looking at a regional scale. For example, we have like a hilly region which is prone to landslides, and we try to kind of see how much this particular area is prone to landslide and how much of the slopes in this area are particularly prone to landslides. And then we kind of focus at the very end into a very specific slope, which we know is notorious to being susceptible to landslides. And then we try to assess how critical it is. And if a failure would happen, what would be the outcomes? So let me kind of take you back into, when we talk about a slope has very, very critical, complex, I would say, behavior. So simply, if you draw a very, very simple slope, right at the very top, you can see, because the slope is kind of going down, there is something which is compressing on the top of the slope. And then you see that it kind of slips over something which is like a pie of a circle. And here you can see that it basically shears. So you have two surfaces which are basically shearing against each other. And then here you basically can see something tensile. You basically see the loosening and the soil kind of comes out from here. So you have a very complex mechanism in hand when you say that you want to assess the stability of a particular slope. But eventually, what is the main thing that you're looking for is that you want whatever is the load coming onto the particular slope, which could be due to infiltration of rainfall, due to earthquakes, due to construction of a building, should be less than the maximum that the slope can take. And this is what we define as the factor of safety. So that's how we, in a very simple term, say whether a slope is safe or not. And that is where the numerical model can basically be useful. So when you talk about modeling a particular slope, you need to have some input so that you get the required output. So what could it be? The first thing, the geometry of the slope. How is the topography? What is the kind of material in the slope? Because that decides how this is going to react with the external conditions. The hydraulic conditions, how much of rainfall, what is the groundwater level? That is the two conditions which predominantly are one of the biggest reasons for kind of exciting landslides, rainfall and the groundwater conditions in a combination. And then intuitively, we know that the presence of vegetation can inhibit or make the slope a bit more stable against failure or being critical. So this is an important condition. And what is the boundary conditions? Like, do you have a weaker slope surrounded by rocky terrain around? So these are the boundary conditions which again decide how the slope is going to behave. So whenever I talk about the toolkit, what do we need? The tools that we need to kind of model this behavior is, first, as I said, you have the slope made of something. So we need to understand what is the behavior of this particular material to kind of decide how it's kind of going to react to different external conditions. And then how do we kind of decide this? We have to be there in the field. So we know how we want to map the behavior of the material. We choose a particular constitutive model, which is the first part, which can capture the behavior of the material. Then you definitely have to be in the field to get as much as data as possible from the field, from getting samples to also kind of having data from its sensors, for example, if they are installed in the field. And then you go back and plug it into a numerical model. And then you ask the numerical model what is the conditions which is not visible to the naked eye. or to the sensors or to the field investigations. Then when we talk about like ground investigations, which is very, very critical, especially for any other field in the domain of civil engineering, for landslides, it's also again critical. So there are two ways. So you have to go to the field, you have to drill samples, you have to conduct some tests, probably conduct some install some sensors, collect some data from this. So that is an intrusive method. But nowadays, with advancing technologies, you also have non-intrusive methods, which kind of Shantanuji included with, for example, the LiDAR surveys. You have other ground penetrating models. You can do a lot of things now with the drones, with thermal imaging. We kind of have seismic methods to kind of assess what kind of strata is existing in the particular slope. So this can help us identify where is the water level, what kind of stratification do we have, and also some basic idea of what is the kind of material which exists in the slope. And then we basically, as I said, you have to do your best to capture the material behavior. So we have to know what is the strength of the material that we are trying to model. So usually the best way is to get a sample and to have it tested in the field, in the lab. So I don't go into the details of the testing, but usually there are different kind of test conditions which mimic the conditions in the field, and you try to see the maximum that the material can take. If you don't know what that material can take, you cannot assess how safe it is in the ground conditions. It's in the conditions that it's actually exposed to in the field. Now, this could be tricky, like getting samples from the field could be tricky when you're talking about a huge region. But nowadays, we're coming up with newer technologies. To quote, I would talk about infrared thermography. So you collect samples from certain areas, then you kind of relate the material to its thermal imprint. Like this kind of material would have this kind of a thermal imprint. And then you scan you do an infrared thermography throughout a huge area. You get a thermal scan, and then you correlate it to the samples that you had and what thermal scan they had. And then you can kind of have an overview of an entire area of what kind of material exists, because this is very, very key to start modeling any kind of slope at a regional scale or at a slope scale. Now we move into what do we say when we basically talk about modeling a slope. So the classic thing that we know is a limit equilibrium method. So what do? You have a particular slope, you assume that it fails along this blue line, and you basically counterbalance the forces which are acting on it, which are destabilizing it, and the forces which are trying to stabilize it. For example, friction along the slope and the component of for example, the gravity is trying to push it down, and the friction along this slope is probably trying to keep it in place. So we just counterbalance the two forces, and as long as the stability forces are higher, you are safe. So that's how we, in very simple terms, we assess a stability of a slope. So in limit equilibrium, what do? If you're given a particular slope, you draw many such arcs, and you try to see which arc is the worst. Like where do you have the least stability forces or the highest instability forces, and you say that this is the most critical condition, and that is what you term as the factor of safety of this particular slope. So I'll look into an example which is out of Kerala. So we talk about this Alathur particular area which had a landslide, and we basically kind of try to look into the stability of a particular slope where it occurred. So we used, like in this case, a particular software called GeoStudio was used. It's not my work. It's a work which I'm trying to quote because it comes from an Indian scenario. So it's better to kind of correlate. So they used like GeoStudio with seep flow and slope flow. The whole point is initially you take the slope, you subject it to different infiltration conditions. For example, for rainfall, how the groundwater changes. Once you have a condition which you want to assess, you take the groundwater conditions or the hydraulic conditions and you plug it into a stability calculation. And then you assess, you draw different arcs and you try to assess what is the factor of safety. So these are two decoupled processes. First, you take into account the hydraulic processes. Once this is done, you plug it into a factor of safety assessment. And for particular slope, you'll get a factor of safety after it's being subjected to any kind of rainfall event or change in the groundwater conditions, for example. And for example, as I said, for the seep or the hydraulic conditions, you need to know the hydraulic properties. And for the stability of the particular slope, you need to know the parameters for the particular material or the slope material properties. And you club them together and you get a factor of safety. So as I said, first you kind of assess what is the groundwater conditions, and then you plug it into another module where you assess how safe the particular slope is in particular groundwater conditions. Now, what happens when you actually have like a case of a, okay, these slides are kind of missed out, but when you have a 3D conditions, for example, you're trying to design a mitigation measure. So the method that we spoke just a couple of minutes before, the limit equilibrium method, is basically a 2D model. So you cannot assess, for example, the effectiveness of a mitigation measure, which probably is existing in a 3D scale. So then you think that you have to move to a 3D level to be able to better capture or better get better insights from the numerical model. And then why is it also important? Like 3D is probably going to be the way of nature in the coming future, because the computational power is increasing. Also, there is a lot of focus on like BIM. So people want to have all the data integrated into a particular 3D model. Imagine that you have a huge region where every data is kind of integrated, and then you can kind of, you have a 3D layering, you have sensor information, you have information from ground investigations, you have information from LiDAR scanning. So everything is kind of in one package, and you can kind of click buttons and probably assess the areas for stability where you are curious. The main point is you reduce the number of assumptions. And this data kind of exists right now in pockets, but with advancing computational capacities, this is probably going to be the future. So 3D is eventually going to be the way of life. And then we move into, when we talk about 3D, we have to start working with the finite element modeling, one of the frameworks where we basically let go of this arc method of analysis, but we can look into 3D geometries, and we don't have to predefine where the slope is going to fail. The slope might not always fail on an arc. It could fail, for example, on a completely different shape. So in this case, in this particular framework, you don't have to tell the model how the slope is going to fail. It is going to predict how it is going to basically fail. And as you can say, you can model also changes. For example, Shantanu sir said that during construction of a mitigation measure, while they are constructing, there are changes in the topography, and this affects the whole process. So in this case, you can actually model this in a numerical framework, that if you excavate for the construction, what are the changes in the slope, how you can better basically capacitate yourself so that you're not surprised or open to surprises. And what is the main advantage of finite element modeling is, in the first case, we had to do the hydraulic modeling separately and then put the safety modeling. In this case, for example, there is any kind of slope. Again, I quote two slopes from Kerala. While the rainfall is happening, you can actually assess how the safety factor of the particular slope would change. While the rainfall is happening, the infiltration is happening, the runoff is happening. So this gives you the capacity to do it in real time, kind of real time. They're both coupled together. And for example, you again need decently good enough input parameters so that you have realistic predictions. So as I said, in this case, you can see the factor of safety basically changing with date and with rainfall intensity. So the blue bars basically show you the rainfall intensity and the factor of safety, how it changes. So as soon as the rainfall intensity increases, you see that the factor of safety is basically changing. So you can kind of assess, you can look into how the displacements in the slopes are also changing with rainfall. So not necessary that there is a failure, but there is too much of displacement which might not be good for serviceability, for example. So that can also help you assess this. Now I only bring you to all the colorful pictures of what numerical modeling can give you. In this case, there was a small erosion which triggered a progressive kind of failure. So we were able to capture this. A small ravine, which is very common in a hilly terrain, there was a small erosion at the banks of this particular ravine, and how this kind of triggered a progressive failure. And then we kind of tried to, this is another case where there was a particular, this is a case from Japan, there was a particular expressway running in a hilly terrain, and there was some sliding material which they were suspecting was going to go loose and create a debris flow. So we looked at a 2D level, how this debris, how unstable it was and how this debris was going to move. And then we could also see in a 3D terrain, how this debris, if it got released, how it eventually moves in the topography of the area and how it's going to impact with respect to the runout. So we can do very fancy, sophisticated movement runout modeling in a particular terrain. We can also simplify the runout modeling by using 2D, like depth average models, where you can take a plan or an elevation plan of a particular area and you release some material and you try to see how much it kind of expands into or flows into the particular area, which is very important, for example, for debris flows. So for this, we have an in-house model called as BINCLAW. So the main thing that I want to highlight to model how much it expands the flowy material depends on how you map its behavior. Water, for example, is Newtonian, but soils, debris flows, they are very tricky. They are non-Newtonian. They could have a viscostic kind of behavior, viscous behavior, or somewhere in between. So we have to map how it behaves. And then, for example, in this case, there was a failure of a particular slope which eventually reached a water body and created a mini tsunami in this particular lake. So we tried to see if the failure happens, and it did happen. And then we were able to see the predictions. The red outline is what was observed in the field after the failure and how the runout modeling predictions matched with what had happened in the field. So just to give you or make you believe, the main question is when we talk about at a regional scale. So this is always tricky. So at a regional scale, we want to know the stability of individual slopes. Then what happens if something is unstable, something fails? Then how does the runout happen? So there is a very nice software called as Landflow, which is being developed in some of the universities in Korea. So this kind of combines the modeling part. So the first part is it will assess the stability of different slopes on a regional scale, coupled with infiltration. So it is coupled. So you get the advantage of having rainfall subjected to it, the change in the groundwater level, how is the stability. Once something is close to 1 or less than 1, you can assess how much is the volume is basically becoming unstable. And then this volume is used to map the runout in a particular area. So it combines everything into one package, which is very interesting. So in this particular small simulation, you can see how it shows that you basically start with a particular instability with a certain volume being released and how it moves over a terrain. But the main lacuna of this particular model right now is it's not being benchmarked. So we need this kind of data from some regions, at least good data, where you can benchmark what this is predicting is actually close to the field conditions. And I'll leave you with some interesting questions about like variability. So the rainfall conditions probably are also variable with the changing climatic conditions, and also the ground conditions are very variable. So we eventually have to move to more probabilistic kind of analysis, where you kind of are uncertain about the rainfall, uncertain about the ground conditions, and you have to move more from a deterministic to a probabilistic framework, where you talk about what is the probability of things happening if the probability of material is so and so and the probability of rainfall is so and so, from one extreme to the other extreme. And at the end of the day, I would say, as I highlighted in the beginning, nothing in itself is completely enough to solve the problems at hand. So if you have numerical modeling, it helps you kind of plan susceptibility for physically based models, where you can assess which slopes are basically prone to failure. you can basically integrate it with sensors to kind of develop early warning systems alongside a predictive model. For example, if you have sensors in the field, you have satellite data from INSAR, you model it, you kind of benchmark it to the measurements from the field. You have an active model now which you believe, and to it you can feed future conditions which have still not happened, for example excessive rainfall, and ask it to predict what will happen. So this can go into a predictive model, also helping you develop early warning systems, and also for design of mitigation measures. As I said, you never know, once you start constructing a particular feature, you never know how the stability of the slope changes. So because you cannot do it on the field and then expect what are the changes, you can basically use a numerical framework to help you assess well in advance what could happen even during the process of the construction of a mitigation measure, and also optimize the design of the mitigation measure. So that brings me to the end of my talk. So there is a QR scan which brings me to my LinkedIn profile. I think we don't have time for questions, but feel free to drop me questions via LinkedIn too. I'll try to answer them in the coming few days. Thank you. Thank you so much for the opportunity, Aditi. Much, much appreciated.
Thank you so much, Dr. Sparsha. Really interesting insights. Technical, on the other side, it is also reflecting the required understanding, especially in the case of factor of safety, intrusive and non-intrusive methods, and also about stabilize with your models and that. Thank you so much, Doctor.
Thank you so much, Vishal.
I think Dr. Yunus is here. Sir, are you able to restart?
Yes.
And
Am I
please
audible,
share.
Vishal?
Yes, we can hear you.
Okay.
And
Let me share.
as looking at time, request for summarize in 10 minutes.
Sure.
Thank you. If possible, full screen, please.
Yeah. Thanks, Vishal, again. Thanks, AIDMI and Miyamoto for the opportunity. The last two presentations from Professor Shantanu Sarkar and Sparsha has briefly explained all the basics. Today in my presentation, I will cover the critical lessons from Wayanad landslides, which is a hot topic today. So we did a comprehensive fieldwork in the region. And everyone knows this. It happened on the 30th July 2024. About 239 people were killed. 59 are still missing under the debris. And more importantly, about 1,500 houses were destroyed in the downstream part of this particular area. So we did a comprehensive fieldwork to know that what happened in this location. This area is close to my heart as well, because this is my hometown. This basin comes within my hometown. So we did an initial study in 2018-19 after the major landslide happened in this region. You can see that this Google Earth image, you can see that this is the present Mundakai landslide that happened in this 2024 July 30. But in 2018-19, after the rainfall, you can see a large amount of debris slides happened in these channels. So this is the Chaliar Basin, one of the fragile part of the Western Ghat. And when we mapped into after 2019, how many landslide happened in this particular basin, we could find about 3,000 landslide, and majority of them are large debris flows. So this is an interesting area for landslide research. And we have in our old publication, we summarize what are the drivers of the landslides in the Western Ghats. One of the key findings is that the stream power is one of the major topographic attributes that contribute to the initiation of the debris flows in the region. And as I was working on this particular region, I asked my master student to keep a look on the Chaliar River, what happening in the river turbidity. So we have started collecting the data from this location of the Chalya River, this is the source of the landslide where the debris flow happened on 30th July. So we started collecting the turbidity level from 3 stations about 80 kilometers down of the source area. And this is the results which we got from the 2nd July. My students started collecting the data. And the peak value of turbidity before the event, you can see that it is about 80 milligram per liter. But in the event day, the turbidity rose to about 10,000. So that much amount of sediment was deposited in the Chalya River. And immediately following this event, so you can see within 48, almost all this the river turbidity washed into the Arabian Sea. So this is a very steep gradient channel, and we could see a lot of turbidity during the event, and immediately it washed out. Now, there were after the event happened, there were few questions came into our mind. So what were the primary triggers factors that triggered this landslide? Why was the impact of this landslide so devastating? Because even in 2018-19 as well as in 2020, much bigger rain happened in the region, but some of the landslide was not that devastating like 2024 one. So why was the impact of this landslide so devastating? And was there any mitigation? Because this is a fragile area, as I shown in my previous slide. This is a highly landslide prone area, and since a lot of studies has taken after 2018 and 19, so was there any mitigation measures available in the region? If so, what happened to that? So that's the few questions which came immediately after the event. So we look into the rainfall pattern for that particular days, 29 and 30. So the cumulative rainfall was for the 2 days was 586 millimeters. So that's almost 20% of the region's annual precipitation. So one of a PhD student from a different institution asked me a question. Okay, so the 586 millimeter of rainfall happened in Wayanad, in this particular region, but why only this particular landslide happened? Why were no other landslide happen in the surrounding slopes? So this is an interesting question. So this motivated us to further look into the triggering factors or the conditioning factors of this landslide. We look into the previous satellite images. So you can see that in 2017 December image, this is the white polyline are the present day, the 2024 30 July debris flows boundary. The source area is here. So there is nothing in 2017-12, but in 2018, so there is the major rainfall happened in 2018. So what happened after that we checked, you can see that there is a minor debris flow happened just above the crown of the present day landslide. And in 2020, there again another major debris flow happened somewhat down of this crown. So that initiated a crack to form in the present day crown location. So you can see a crack, well-developed crack in this location. This is caused by the destabilization of slope due to the undercutting. Now, if you look back into 2024 April image, you can see those cracks become widened. And on the day of the 30th morning, so since the rainfall was too heavy, the rain seeped into these cracks and further widened, and the instability of this that we believe is the major trigger of the Wayanad landslide. Okay, so this was the trigger, but why this landslide was so devastating? Because earlier in 2000, there was a landslide here in the same channel. So these all are channelized debris flows. So in the 2020, when the landslide happened, this debris was confined within the banks. But in 2024, you can see that it washed out completely the sediments from the upper part of the river channel. So this look into see what was happened and why was this landslide so devastating. we look into the, so we fly a LiDAR and RGB sensor in a drone. And this is the top part, the ground part of the landslide. You can see it's a planar failure caused by the cracks that widened after 2020 that resulted in this particular failure. But you can see these these large boulders that is deposited here. You can see there is well-developed joints here, which you can further see from these images. This particular region is highly vulnerable in or fragile in case of lithology as well. So there is a set of joints, parallel set of joints, as well as crisscross joints present in this bedrock. And furthermore, when we closely look into the characteristics of this lithology, this is mainly the hornblende biotite gneiss. It's a gneissic terrain. And this gneissic terrain, when it mixed with water, it immediately, so those feldspar that is present in this in the hornblende biotite gneiss immediately break up and when the water is mixing, and it causes a lot of erosion here that result in the development of large soil thickness. Apart from the joints and the weathering, we can also see shearing is another important reason. So here we can see that this part of the rock, when compared to the other locations, are highly sheared, caused by the stress, regional stress that is happening in the region. So these result in the formation of huge thickness of the soil up to 30 meters. So when the feldspar is mixing with water and when it erodes, it forms the colonnade. So this is the XRD profile which we studied after the landslide when the soil sample is tested in our laboratory. And this is the soil profile. You can see that at places the soil thickness goes up to 31 meters. And in the top of the ground part, the soil thickness ranges 0 to 6 meters. So we did a digital elevation model subtraction from the post-event minus the pre-event, and to see how much amount of the sediment is transported. And what we identified is that the amount of sediment that is transported is about 5 million meter cube. That is comparable to other large events that is happening in India, such as the Kotropi landslide in 2017. And the velocity, when we run the RAMS model to see how much was the velocity of this debris flow movement, we find out the debris flow movement was about 28 meters per second. So that is too high to carry these mobile substances that is coming with this heavy precipitated water. And other reasons which we find why it is so devastating is that multiple damming has occurred in this particular area. One of the location we believe is this particular narrow channel of the river where the maximum width is only 3 meters. Where other places you can see the river goes up to 100 meters. The another location of the damming is the old Kujirimatam, one of villages here. So this village mostly devastated during the event, and there was a bridge here. So below the bridge, most of the material, the debris dumped, and again created a damming effect. And another damming effect in a nearby waterfall that's called Seethamkundu waterfall just below this Kujirimatam bridge. So such 3 damming location was identified, and when these dams immediately breaches, they cause the devastating run-up and the destruction of the buildings there. So such a damming effect was one of the major reason what we believe is the devastating effect or the cascading chain process. So here we see the run-up of the landslide. You can see that in the right bank, the largest height noticed is 32 meters, and in the left bank it is about 28 meters. And these are some longitudinal profile we developed for the region, and we find that lot of cascades or small nick points are present in this river, which also resulted in the enhancing the river runoff. Then we also looked into was there any mitigation measures taken. So here is a YouTube link which I'm showing that from a major news paper, that's Manorama News. They reported in 29/7/2024, the day before the event, from the nearby the same channel. This reporter is saying that heavy rainfall is happening in the region. The local self-government has put a warning there and asked the people to evacuate and not the tourists to come into this region. So there was an mitigation measures taken because this region is like previously also was failed in 2020 as well as in 1984. One of the saddest part is that since the mitigation was taken, people were evacuated. One kid who was living in this particular house, he moved about 5 kilometers downstream of this particular location, and during the event, when the event was happened, his house was actually safe, whereas the 5 kilometers below this location where he stayed, it washed out and the kid died. So this is the saddest part, that nobody think about this unprecedented run out of this particular landslide. So particular that the most impacted part of the Churalmala settlement is about 80 meters away from the riverbank and had not experienced the direct impact of landslide in over 1 century of its existence as human habitation. So this is the first time such a like 8-kilometer run out of this flow is happening in the region, and nobody was thinking about that. These are some cross profiles which we developed from the upper part of the river channel, middle part, and in the lower part. You can see the erosion in the upper part was about 30 meters. And the deposition in the lower part, you can see up to 10 meters of the deposition happen in the some location which washed these buildings. There were several news reports which were also talking about the anthropogenic activities, whether it was related to anthropogenic activities that contributed initiation. Our simple answer is no, because this is a pristine forest, and we have conclusively said that this is happened due to a crack that is developed and widened over the last 4 years. And you can also see in this photograph the large amount of debris that is deposited here from the past events. So historical events, you can see large boulders cemented in the small, finer grain size. And when we talk about this event, I could remember about this Chamoli event. This happened in a similar manner. In 2016, there was a large-scale landslide happened that destabilized the upper slope and finally triggered the 2021 Chamoli event that killed again another 200 people, those who were working in the hydropower plants. So this lead to the following key takeaways. The precursors or precursor events are key to early hazard detection and mitigation. Again, nobody think about such unprecedented runout of landslides. So the scope of runout modeling should be carried out to needs further increased. And any warnings that is provided should not be taken lightly. And for such areas, these fragile areas, you can see multiple events happened over the time. We need a real-time monitoring system to mitigate future risks. So this is all about my presentation. Thank you for listening.
Many thanks, Dr. Ali. It's really thank you so much. Looking at time, we already passed, but on the other side, would like to open floor for question, if any, and I also request all of you, if possible, keep your camera on. We will take some snaps in between during this question answer. Any question? you can use chat box or can speak out. I have received a couple of questions, but before moving to that, would like to ask Upan. Okay, so I have received three direct questions. One is, what are the primary data gaps that hinder the accurate numerical modeling of landslide at both slope and regional scales? And if our speakers would like to.
I think Professor Shantanu Sarkar and Sparsha can.
Can you please repeat the question? Is it on regional scale modeling or?
Dr. Sarkar, can we?
Can you repeat the question, please?
Sure.
Yeah.
So the question is, what are the primary data gaps that hinder the accurate numerical modeling of landslide at both slope and regional scales?
Okay, for slope stability, as Dr. Sparsa already told about this basic data for site specific stability, as I understand as from the geological background, is the slope profile is very important, and the strength characteristics, shear characteristics, shear strength parameters are all through which we can do the stability analysis. But main problem is to get the good data of the triggering factors. If I say rainfall, as Dr. Sparsa told, people take the data of some saturation level and do the analysis part. But as we know that the start of rainfall, it is also a dynamic process, that how it is saturating the slope slowly. So on the basis of that, probably the accurate modeling can be done. I think better. I think Dr. Sparsa can reply this question because he is working on
Yes,
the
I was
modeling.
about to request her. Please, Dr. Sparsa.
Right. Yeah. Thank you. I think Dr. Shantanu kind of rightly pointed out that it's a dynamic process. So we need to kind of understand that. But at the same time, we need to start somewhere. So I think, as I say, like if we lack data, it's not easy to acquire this kind of data. So how the material behaves is one necessary thing that we should at least make a good engineering judgment or assessment of it. And the other thing is about the hydrological conditions, because that's the main triggering factor. So we should try to kind of capture that as much as possible. But at the same time, just because we cannot replicate what happens in reality, we should not shy away starting it. So that's why I think thinking more on a probabilistic kind of framework is nicer, because then you can take all the extreme conditions and probably prepare for the worst in case this suits even more better, because uncertainty and lack of knowledge is prevalent everywhere. For on such scales, it's kind of difficult to have such kind of a data, because it will take years or at least a lot of hard work over a couple of years to kind of have access to it. So a probabilistic framework with good engineering assessment and judgment can be a starting point, and you keep on adding to it and improvising the model.
Thank you so much. One another question, I think it's to Dr. Yunus, but open for all expert. What specific mitigation measures would you recommend to reduce future debris flow risks?
I think we need site-specific landslide runout models in almost all the populated areas below the mountain. So this is highly recommended. And apart from that, our present day the landslide, the warning forecast for the rainfall, especially for this particular region, Wayanad, when I say there was no alert issued for the rainfall forecast. So this was because most of our forecast warning is somehow failing in orographic regions such as like Western Ghats as well as some part of the Himalayas. So we need to further revise our modeling taking into the regional aspects on the rainfall as well as on the runout modeling. This is some of the initial measures which we can start with.
Thank you so much. Is Divyaji here? You raise your hand, and then now I'm not able to see. If you are here, you please share your question. Hi.
Yes. So I have question with Dr. Sarkar sir. The way he and his team is working in the Uttarakhand, doing this all exercise to understand the vulnerability and try to connect with the safety measures and also how government can intervene. Is similar kind of interventions happening in Himachal also? I mean, I just want to know because I never worked there. And the second question is for, I mean, if any other panel member or sir can answer, how we can connect the local level efforts, the community level efforts, maybe related to livelihood or maybe related to some other interventions, connect with the mitigation of any kind of landslide. So these two questions I would like to ask.
Okay, it's a good question. The first is that I do not. I'm difficult to comment on what Himachal Pradesh is doing, but there's a certainly a huge loss, due to landslide last
Yes.
year also and this year also. I mean, Himachal has got a lot of problem. Landslides more frequent and more disaster as
Yes.
with respect to Uttarakhand this time.
Yes.
And I have an interaction with Himachal government also. They are also doing very good landslide inventory map and mitigation measure planning and all these things. But I am not very sure that this what I am planning, my center is planning to do for particularly focusing on the towns, major towns for
Right.
building a database along with mitigation measure is going on. Several mitigation measures is going on for so many
Absolutely.
landslides. But these two three things which I think that Uttarakhand government has, our state has started. I mean, I really very happy that state government is giving me all the support that to build this data and this actually it happened after this Joshimat incident came,
Yes. Yes.
because
Yes.
we are not getting any data. Then we are brainstorming and then decided that let's do.
Yes.
Though it's taking a lot of time for so many administrative approval and so many things are there. But I think slowly we'll build up. And we are in touch with Himachal Pradesh and we have had interactions and probably they are also will be doing such type of.
Great. Great. Thank you, sir.
The
Thank you.
second, the
Sorry.
second one, the second part which you are trying that with NDMA, we are also trying to reach to the people at the very panchayat level and village level, so that we can educate them for. I mean, particularly for landslide, I can say that we are working on that.
Okay.
Thank
Thank
you.
you.
There is one question from Loy Rego. Thank you for joining, Loyji. What are the mitigation measures, especially from other countries, that can be taken in advance to minimize the impact? And if you would like to reflect any example, please. Thank you. Dr. Sparsha.
I think if I could put it, I think we should not focus on what the other countries are specifically doing it. I think that the main thing to understand is each landslide has to be understood. What kind of a landslide is it? Like, you cannot apply a debris flow solution to a typical slow moving landslide. So we need to assess what kind of mechanism is at place and what kind of would be the outcome of a failure. And then we try to look into the mitigation. Also, another thing to note is we have to optimize the mitigation and where we want to install it. In areas like Uttarakhand or Himachal, there are huge regions which are prone to it. So we have to prioritize, first map which areas are prone and then prioritize which are critical and then apply the mitigation measures. It's easy. If you basically construct a heavy earth wall or a completely cut and cover kind of tunnel throughout, for example, a linear infrastructure along the Himalayas, it's going to be a robust solution. but that's probably not what we are looking for. So the main key is to kind of identify the areas and what kind of flows are we looking into, and then install or try to develop mitigation measures at key points. But for debris flows, for example, the flexible barriers is something which is widely, extensively kind of used throughout the Alps, for example, to kind of mitigate. But if the flows are way, I would say, more in volume, more impactful, then you usually have to go for covered corridors, for example, along roads. But also the other key thing is, here a lot of places the governance has accepted that in some areas it is no longer possible to mitigate, so they're even ready to move villages. But that's a different scenario for us because we have bigger populations, bigger areas, and probably a lot of reluctance to have such kind of a movement. So in some areas it's also important to accept that it is beyond mitigation capacity, which is difficult, which is unfortunate. But we also have to look at that one extreme where we probably have to look for solutions outside technical solutions.
Thank you so much. So we will try our best to respond by later on communication, but I can also see Dr. Menon is also here. Thank you for joining, sir. How I can say no, please.
Thank you very much. I must compliment Miyamoto and AIDMI for bringing together such a very distinguished panel of experts. I would like to compliment all the panelists for excellent presentations. Regarding the landslide history and the trends in both the Himalayas and also in the Western Ghats, there are many similarities in terms of what is actually happening, whether it is Himachal Pradesh or Uttarakhand, and also in Kerala and Karnataka. We find that there are many similarities because of the way in which human interventions are actually also, aggravating the crisis, whether it is road constructions or tunnel constructions or, the construction of resorts and hotels and other things on the hill slopes which are unstable, especially given the landslide history. I think we need to also be very clear that mining, quarrying, and the kind of deforestation and human interventions, including sand mining, has actually had adverse consequences. So I am not sure whether this whole interpretation of the Wayanad landslide as a debris flow alone would actually be acceptable to the ground realities, because it is also a landslide and also rock falls and debris flows and mud flows, which actually had a huge runout of 8 kilometers. More devastating than, as Dr. Yunus himself mentioned, more devastating than the Malpa landslide of Uttarakhand. So I think we need to understand lithology, geomorphology, hydromorphology, soil piping, and many other factors in interpreting the kind of adverse consequences, especially further aggravated by human interventions. I would like to just listen to your feedback. Thank you.
Thank you, Dr. Menon. Any response?
I agree with Dr. Menon. My intention was only to say that the trigger was not by human intervention, but as it is aggravated, the disaster was aggravated by, of course, the anthropogenic activities. And we need to focus these areas for any further disturbances.
Thank you so much. Now, without further delay, I would like to request Dr. Singh, Aditi Singh, to please share your concluding parts. Thank you.
Thank you, Vishalji. So as we conclude this insightful webinar, I would like to extend my sincere gratitude on behalf of both the organizations to our distinguished speakers, Dr. Sarkar, Dr. Sparsha, and Dr. Yunus Ali. Their expertise and valuable insights on landslides, including mitigation strategies, modeling techniques, and lessons learned from real-world disasters have been truly enlightening. Dr. Sarkar addressed key topics such as landslide issues in the Himalayas, landslide susceptibility and hazard mapping, as well as landslide forecasting and mitigation strategies. His discussion emphasized the importance of DRR for Hill Township and the necessity to integrate scientific advancement with community-based approaches to reduce risk. Dr. Sparsha's presentation on numerical modeling underscored how precise modeling can aid in risk prediction and resource allocation, providing a critical tool for authorities to make informed decisions about mitigation and response. Dr. Yunus Ali's reflection on the Wayanad landslide disaster illustrated the catastrophic potential of a landslide and the need for real-time monitoring system and post-disaster recovery planning. I hope each of us feels inspired and better equipped to take meaningful action in our respective field to mitigate landslide risk and enhance preparedness in vulnerable areas. Now, as we conclude this session, I'm excited to inform you that we are planning our next webinar for the third week of October. So stay tuned for the details. And we look forward to seeing you soon with a fresh topic and inspiring experts. Once again, a heartfelt thanks to all the participants and have a pleasant day, everyone. Thank you.
Thank you, Dr. Arif.
Thank you.
Thank
Thank
you.
you so
Thank you
much.
so much.
It's
Thank you.
really
so
very
much.
useful. Thank you, Tahirji, for joining.
So you are closing the session? Can we?
Yes. Yes.
Thank you very
We're
much.
closing the
Thank you.
session. Thanks,
Thank
everyone.
you. Thank you,
Thank
everyone.
you.
Thank you. Bye.
Thank you.
Thank you.
Oh,